Hey, Michelle.
Yeah, we're getting ready to go live. Are we bringing the pre-roll? So stand by, okay?
Sounds good.
Okay, just stand by. It's all set. Otherwise, once the show starts, we'll introduce you, and we can go right to the slideshow.
Sounds good.
Born in Silvermoon, where the magic flows, in the land of mages, where the ancient wisdom grows. So here we are, in the land of dreams, with Carmen Miranda, in the moon's beams, in the dance of life, in the magic's glow. In Silvermoon, our love will always grow.
Good evening, everybody. Tonight, of course, is going to be a special. We didn't have an intro song for the special tonight. It's Wafters is going to be. We're going to be going into some a little deeper science 101, for lack of a better name. How you doing, Wafters?
Doing good. How are you?
I'm doing all right. Let me just get this thing ready to start. So I'm going to go to the slideshow.
Yeah. So you're gonna share
And
the
I'm
slides?
going to manually start this. So let's see. So I'm back on page 1. So we're going to start because I know you guys. There are going to be a lot of questions because a lot of this stuff is new to a lot of people. And
Yeah.
so let's get
Yeah. I was hoping to cover a lot of
right.
bases,
Right.
without getting too complicated.
Exactly. So that's
That was
what
the
we're
that
going
was
to
the
discuss
challenge.
today. It's called Quantum Physics Basic Rundown.
Yeah. Yeah. So you guys, if you're ever interested in quantum physics,
So just let me
is...
know when you want me to change to the next page. So
Yeah. 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 That sounds good. Yeah. So the goal here is to basically have you leave this show with a little bit more understanding of what quantum physics actually is, and what some of the nomenclature is, some of the vocabulary and concepts. So it's not so alien. Um, will you be a quantum physics PhD after this? No. I'm not going to really dive into the math. There are some equations in here, but they're mostly decorative. I'm not going to go into any derivations or anything like that.
so basically, this is kind of like some like introduction to physics at a high school level, or maybe middle
Yeah.
school level.
Yeah. I try to make it sort of like a high school level
Right.
presentation here. Pretty informal. I'm not going to start from first principles or anything. And I kind of have it ordered, not perfectly ordered, but sort of ordered by history, like how things were discovered and what the rationale was at the time, that sort of thing. Yeah, so why don't you go to the next slide? Do the same on my end too. All right, so instead of saying, what is quantum physics, just have the question of where is quantum physics, because it's just about everywhere. You could argue that chemistry is quantum physics. I mean, you're dealing with atomic structure, you're dealing with electrons and all kinds of things there. Chemical reactions are physics, after all. There's nuclear reactions, or sometimes called nuclear chemistry. And what's going on there? You've got protons and neutrons, and that's where you get nuclear reactors. Things that power cities, power. If it's not coal or solar, it's
and we both know that chemistry is, of course, used in a lot of modern life.
Oh yeah.
And that's the part we probably understand. For example, like how water is the universal solvent that can clean up most things.
Yeah. Yeah, it might take a while, but yeah, it does.
Yeah.
Yeah, it's chemistry is anything to do with any kind of atoms or molecules. You're going to be dealing with chemistry, and that of course extends to things like medicine.
Mm-hmm.
And then I mentioned solar panels. Solar panels are quantum. I'll talk about that too. So if you've got any solar panels in your house, congrats, you own some quantum physics.
Right.
Yeah.
That's related to solid state electronics.
Yeah. And then of course lighting depends on quantum phenomena, and even things like classical computers like transistors use quantum effects, namely what are called quasi-particles. I won't really talk about that here, but I wanted to mention the terminology because you may come across it if you're ever studying like basic computing.
Mm-hmm.
You want to switch to the next slide? Yeah, so the overview of this is going to be like the history of discoveries, how they're interrelated. Hopefully uncover, in this process through history, we uncover more and more of the nature of reality.
Thank you very much for the $3 donation, Star Trek. Very much. Thank you very much. I will
Thank
try to give you guys
you.
thank yous when I can, but I will try to disrupt Wafters.
That's okay. That's okay.
Okay.
Yeah, thank you, Star Trek. Well, over the course of time, we uncover more and more the true nature of reality. Will we ever get to the actual truth? Probably not, but we learn more and more. And I'll talk about the concepts in quantum mechanics, quantum physics, and the applications.
Right.
And here I have a little decorative Bohr atom. We'll talk more about that as we get there. So why don't you go to the next slide? So what is the matter? What is matter? The Greeks, Leucippus and Democritus, actually thought of atoms in like 400 BC. Right, so this is an old concept. Basically, the reasoning though is philosophical. There wasn't really any scientific reasoning. It was just purely philosophical. Like, you can't cut something forever. You can't just keep cutting it and keep cutting it. You gotta end up at some kind of infinitesimal little piece of something. And so the word for indivisible or undividable in Greek is atom. That's where you get the term atoms.
Right. And it's basically, for a long time, the atom was the smallest conceivable component.
Yeah, and they weren't even sure what it would actually look like, what the structure was. There was some folks that thought it was like a infinitesimal point, and there's some folks that thought it had some kind of finite size, things of that nature. There's a lot of debate because it's purely philosophical. They didn't have ways of probing this sort of thing yet empirically. The science just wasn't there.
Right.
But that's where the word atom comes from, and we'll see it resurface later. And other than that, there was a lot of people that disagreed with this idea. They thought that matter was just a continuous substance, but maybe there was some elements. You can go to the next slide. And this is where our boy Plato comes in, around 420 BC, 420. He came up with the idea of Platonic solids. Like, these might be the shapes of the atoms. And you had like the elements of fire, air, earth, water, ether. This is where a lot of alchemy came out of, which eventually gave rise to chemistry.
Right.
And again, this is like 420 BC, so thousands of years ago. Right? You can go to the next slide. And that was the end. That was the end for a while.
Really?
And then you could go to the next slide.
Until Atomic
Yeah.
Theory.
Yeah, until Atomic Theory with John Dalton in about 1800 AD, 1803. Where he's experimenting with gases and fluids, combining things and discovering molecules, and found that there must be some kind of indivisible pieces with specific mass ratios. And this is where we get the more modern idea of an atom. He actually took the word from the old Greek idea and repurposed it for this. So it's came full circle in a way here. And here you have the one of his original table of elements. This is not a periodic table of elements. A different guy came up with that. But this is where he's cataloging the different elements based on combinations of mass ratios and that sort of thing.
This is kind of an offshoot from alchemy. This is
yeah. The chemistry is that's true.
In fact, the word alchemical and alchemy almost the same root. So
yeah, same root word.
Yeah.
Yeah. You can go to the next slide. And then some 60 years later, you have Dmitry Mendeleev, and he arranged these elements by mass and reactivity. And this is where you get the periodic table of elements. On the right there, you have his one of his original periodic table of elements. And this, arranging things like this actually gave it some predictive power. Like you could say, oh, there must be an element here. There's one that weighs 56 atomic units and one that weighs 60. Maybe there's something in the middle there. Those missing bits. And it turns out like it did have predictive power, arranging things like this. And this is where modern chemistry started to be developed.
Mm-hmm.
You can go to the next slide. Then you have this guy J.J. Thomson, and they started to think about like what is the what is this electricity stuff, right? So if you shoot through you basically have a potential difference, some voltage in a vacuum, you get this thing that kind of looks like a light bulb on the right. This is a cathode ray tube, right? This is what old TVs basically used. It's a beam of charged particles.
Mm-hmm.
And later it would be named electrons. This electric current is made of electrons. This is part of what was discovered here. And it has a charge and a mass, right? It wasn't just light. It wasn't light. It was some kind of particle. And it was found that this could charge atoms by either adding or taking away electrons from those atoms, making them ionized. And so the idea here, you get the it's called the plum pudding model, where they thought like the atom was overall positively charged, and you have these electrons that are just dropped in like plums in a pudding. And that was the model for an atom for a while, but it was the first subatomic particle, so to speak. Something that was thought to be indivisible turns out divisible to some degree here.
Right.
And then you can go to the next slide. And then along comes Ernest Rutherford, and he basically discovered the proton. And this is where you get the Rutherford atom drawing, the very famous. This is actually the logo of the Waftcast. Is the atom symbol here. So my channel. This is our unofficial logo. Is the atom symbol. This is actually not what atoms look like, but it's a rough representation. You got the nucleus in the center, and you've got electrons orbiting it. And the way this picture came about was when Rutherford shot what are called alpha particles, which are basically helium, without an electron around it. Shot it at gold foil, and most of them just punched through, but a certain fraction scattered. And from this scattering pattern, he was able to deduce that the atom seems to be mostly like empty space with a real massive center that's very small. And so most of the atomic mass is thought to be in the center, composed of protons. And these are the opposite charge of an electron. So the electrons orbit the nucleus like little planets.
Mm-hmm.
And then about 20 years later, James Chadwick discovered the neutron. So the nucleus of atoms is composed of protons and neutrons. You can go to the next slide. Right. And prior to this, these particles had been seen before. It's just they weren't fully understood. So alpha particles, like I said, you see the alpha particle drawing on this slide, radioactive decay. You have some radioactive nucleus and it sheds an alpha particle. And you have another one that sheds a beta particle. Alpha particle is helium. A beta particle is an electron. And then you have gamma particles, which are photons, particles of light. Right, but the relation to like nuclear fission and fusion was not figured out yet. It was just, oh, hey, we've got this substance that radiates these high energy particles. Interesting. And that's where Henry Becquerel and Mary Curie come in.
Right.
They explored uranium and thorium and basically discovered radioactivity.
Yep.
You can go to the next slide. And then later on, you have nuclear chemistry. This is where you've got Cockcroft and Walton. They discovered nuclear fission. This is where you split an atom. Right. This is a confirmation of Einstein's theory of E equals mc squared. You may be familiar with that equation, at least in terms of seeing it in cartoons and stuff.
Right.
But basically what it means is that mass and energy are the same thing. Okay? So they're just two different manifestations of the same type of thing. And all the c squared is there, it's just speed of light squared. You can think of that as a unit conversion. Okay, so if you're wanting to convert from, say, inches to feet, right, you just either divide or multiply by 12. Right. You could think of converting from mass to energy as multiplying by the speed of light squared. Right, so a little piece of mass gets subtracted from something, you're going to get an amount of energy that corresponds to that. Right, and it turns out it's pretty large because the speed of light is large. And so you have Cockcroft and Walton. They discovered nuclear fission, just dividing nucleus. And then you have Oliphant here, who discovered nuclear fusion, and that's where you fuse atoms together into something heavier. Like that's what the sun does, right? Takes helium, 4 heliums, and fuses them into, 4 hydrogens and fuses them into a helium.
Right.
And this is modeled through a process called quantum tunneling. So you may hear the idea of quantum tunneling brought up when you're watching, like, I don't know, sci-fi or maybe something on Discovery Channel. Basically, you have, you can think of it as a potential well. So let's say you're at the bottom of a hill, right?
Yeah.
And you want to get to the other side of a hill. It's just, you don't want to go around it. You can't go around it. You want to just go over it, right? Classically, in classical physics, you'd have to go up the hill and then go down the hill, right? But with quantum tunneling, you could basically dig a tunnel underneath the hill. And that's what happens at the quantum level. You can go from having a big nucleus to something smaller that would normally take a lot more energy to get from one state to the other, but is able to just pass through that hill. basically tunnel through the hill from one state to the other without needing that extra energy.
Right.
So that's where that terminology comes from. And this, of course, is where you get nuclear power. And nuclear power is basically a big steam engine. That's all it is. You have
At this point, it's all fission based, but on Earth that is. But they are still working on the fusion side. But that's been very hard.
They had a net positive with some fusion, but it needs to be developed further to get it to be more feasible. But I think it's looking promising.
Right.
Let's go to the next slide.
All right. Next slide.
Yeah. This is where, going back in time a little bit here, 1900, you had Max Planck, sometimes called Max Planck, was studying what was known as black body radiation. Now, this is where you have something that's heated to the point where it glows, right? Now, it turns out actually anything heated is glowing a little bit. You just might not be able to see it. It might be glowing in the infrared, right? So you might not actually see it. Like we glow, like humans glow, but we just can't see it because we don't see heat. Our eyes don't detect that. But if you had a heat vision camera, you know, like folks in the military do, you could see people walking around at night easily. You just pick up their heat signature, and that's black body radiation.
Right, because your body is generating heat, infrared every second you're alive.
Oh yeah, but then if you heat it up more, you can get more visible radiation coming off of it. Now, theories at the time trying to explain this phenomena ran into what is later called the ultraviolet catastrophe. And you see this graph on the right here. I'm not going to delve into it too much, but all you have to understand is that the dotted line is what models at the time predicted. And then the solid black line is what Max Planck figured out. So the dotted line assumed that energy was like a fluid. It wasn't particulate at all. It was just continuous throughout, right?
Right.
But that gave you the wrong answer. This did not agree with experiment. Things blew up as the wavelength got smaller. That's where the dotted line kind of blows up to infinity there. That was called the ultraviolet catastrophe. And then Max Planck said, what if energy comes in discrete packets? You call them quanta.
Right.
So discrete packets. And then he did the math with that in mind. And he got this solid black line distribution where it comes up and then comes back down. And that agreed with observation.
Right.
And so it was compelling. It fixed the disagreement. It was compelling because, you know, with this assumption that energy comes in discrete packets, you get something that agrees with reality. So it's like, does energy really come in discrete packets? A little bit of a clue for the future here. And his math that he did, he came up with or found another natural constant, which is now called Planck's constant, which is denoted with the little h with a cross on it, sometimes called h bar. And it's roughly 10 to the minus power of the minus 34 joule seconds, which you don't have to understand what that is. A joule is a unit of energy, second is a unit of time.
Right.
But you might see that pop up.
In other words, it's a decimal point with 34 zeros following a 1. In other words,
Yeah, it's a very small number.
Very small number.
You can go to the next slide. Then you got my boy right here.
Right.
Albert Einstein discovered the photoelectric effect. This is actually what he won the Nobel Prize for, by the way. People think it was for relativity. It was not. It was for this. So it's known for a long time that when light hits certain types of materials, it will produce a voltage.
Right.
And this was called the photoelectric effect. And he investigated it further. Right? So it turns out electrons, discovered by J.J. Thomson, were ejected from this material at a certain energy. And Einstein found that the wavelength of light was related to the energy of the electron, not the brightness of the light. The brightness was only related to the number of electrons, not the energy of the electrons. Right? And so what this implied was that there's discrete photons, particles of light. This goes back to Max Planck,
Right.
where you've got discrete units of energy, photons.
Right.
These are the quanta of light. And here you've got the equation here. E equals h bar, Planck's constant, times frequency. So that's the frequency of the light.
Right.
And then minus a Greek letter phi, or phi. And that phi is just, it's a property of whatever material you're shining the light on. So it's particular to whatever the material is. But the E is the energy of the electron ejected. So this is the relationship he discovered. And this is precisely what photovoltaic cells do. This is what they're taking advantage of, this effect.
Actually, I remember that this was actually kind of discovered by accident when they were laying the first telegraph wires on the cable, on undersea cables. That they saw that in the sun they were inducing a voltage.
Yeah.
Yeah.
Yeah. It's funny. Yeah, the things
It is
discovered by
interesting.
accident. Like the polarization of light was also discovered. I don't have it here. I should have added it in because it's funny. The polarization of light was discovered because a dog peed on a dude's experiment.
Right.
I should have included that. Oh well. So
Okay.
if you want to go to the next slide, you now have Niels Bohr photographed here on his motorcycle. He was a cool dude. He had a motorcycle.
Yeah.
And they were wondering. He was wondering, like, what's going on with these discrete quanta when they interact with atoms? Right? Why does it seem that atoms release these particular values of energy? And so it seems like it's quantized. It's got levels. It's not continuous. Right? The electron is seen orbiting the atom in the Rutherford picture, right?
Right.
But that isn't quite right because there's actually different energy levels. And he figured, well, something's got to be discrete, and maybe it's angular momentum. So there's two kinds of momentum here. You've got linear momentum, which is, when a cue ball hits another billiard ball on your pool table, it's transferring linear momentum to either miss the hole or land in the hole or whatever it is. Angular momentum has to do with spin. Right? So the idea here is that angular momentum is quantized. And from this, you actually get a lowest energy state. And I'll get back to that later, but it was postulated that the electron should fall into the nucleus. It shouldn't stay in orbit. And it was a mystery as to why. And one thing Niels Bohr found is that there's a lowest energy state within an atom. So it can't go any lower than that.
Right.
And he found that the energy levels are quantized because angular momentum is quantized. And here you have a basic equation shown here for the atomic energy levels. You can go to the next The next slide. And these energy levels are precisely why you're able to get spectroscopy. So spectroscopy is basically you're able to identify the chemical composition of something from the light that either absorbs or emits. Right? Because those are the energy levels of the atoms interacting with that light. It's either absorbing them or emitting them. And in this particular illustration, you have absorption lines. So this is something with you're looking at things that are absorbed by the substance, and this can be used to identify it. So you have the on the top there, you have the complete spectrum visible to the human eye, and then you have on the second rung here the absorption spectrum of the element of hydrogen. So these correspond to the energy levels of hydrogen. These are the wavelengths that are absorbed by the atom. And then you can look at the spectral lines of the sun, for example, which is composed of mostly hydrogen and helium. And you see a mix of hydrogen and helium spectra here, because both are present.
Wait, I see that.
Yeah, and so this kind of bears out what Bohr discovered. It can be used to identify substances. You can go to the next slide. Of course, this begs a question that comes from electrodynamics. If you have a charge and you wiggle it around, a charged particle like an electron, you wiggle it around, it's going to create light. It's going to radiate light. And so shouldn't the atom then, which has electrons oscillating around it, wiggling around it, shouldn't it radiate light? And then shouldn't the electron fall into the nucleus of the atom? So what's going on here? What's the deal? You can go to the next slide. Then you have one of the biggest steps. It's asking, well, are electrons particles or are they waves? This guy, Louis de Broglie, not de Broglie, it's pronounced de Broglie, found that the energy levels in the Bohr atom of the electron behave like standing waves. So if you've ever played jump rope as a kid or as an adult, I don't know what you do at home, but you may have discovered this node-antinode pattern that you see in the graphic near the top of the slide, where you can wiggle the rope and get the first mode, and then wiggle it faster, and you get to the second mode, wiggle it even faster, and you get to the third mode. And this corresponds to the quantization of the atom, of the electron levels. So these are not particles in his picture, in de Broglie's picture. They are waves, standing waves that exist in these orbitals. And it also explains why these energy levels are not continuous. They are discrete rings. Right? There's no in between. It's either things exist at n equals 1, n equals 2, n equals 3, and so on. Things don't exist between n equals 1 and n equals 2. Right? And if the electron is a wave and not a particle here, it's not oscillating in the way that I described in the previous slide. So it's not going to radiate in that way. So, wave or particle? Let's go to the next slide. Well, we'll come back to that. Oh, you want to go one up?
You want me to go ahead or backwards?
Go backwards one.
Okay.
Yep, there you go. So observational variables, right? So take a step back for a second. And one thing that was noted about particles, atoms, and subatomic particles is that a lot of them have what are called spin. Now, spin is related to Planck's constant as well. It's basically an angular momentum variable inherent to the particle. It basically makes it a little magnet. It's got a little north pole and a little south pole. And what these two guys found, Stern and Gerlach, is that this is a quantum number, a quantum variable that you can measure, and different measurements can interfere with each other.
Mm-hmm.
Now, this is a very important part of quantum mechanics. So if you have all these, let's say, particles with spin in a gas, let's say, you got these little magnetic particles in a gas. You have figure 1, they can be oriented in any which way. You apply a magnetic field to them, they're either going to align or anti-align. So those are your two states that you can measure. So is this particle aligned or anti-aligned? You can go to the next slide. And so one thing they set up is to see if this is actually a quantized phenomenon or not, is they had a beam of silver atoms that have spin, and passed them through an uneven magnetic field. And so what it did is it either pulled things that were pointed up or pointed down, either up or down. Right? And so you had a screen after this magnetic field, and they're able to show that what you expect from classical physics is not what you see. You get a different result. You get 2 dots rather than a continuous line. So that tells us that this magnetic field basically measures these particles' spin as either being up or down in this in the direction of the magnetic field. There's no continuous spectrum of spin.
Well, this kind of brings it back to the node and antinode you mentioned earlier.
Yeah. That's one thing. Is that it can either go up or down in this magnetic field, and you measure it. So you can think of single particles as either ending up at this top dot on the left or the bottom dot on the left, and nowhere in between. Right. So if you go to the next slide, they took this further. So this image is flipped from the other one, so the source is now pointing the other way. So you got the beam going through this uneven magnetic field, and you get the split beam. You get stuff that's pointed up going up, stuff that's pointed down going down, and you can apply another one of these fields to one of the beams, and you see that the up particles are still up. Okay,
right.
They pass through the second magnetic field and they're still up. There's no Z minus. You see, there's Z plus, Z minus. That's just
that's
up and
because
down.
the Z minus was extracted in the first
apparatus.
It was,
that's right. Now here comes the tricky quantum part. So you can go to the next slide. So what if you rotate the second one so that the magnetic field is pointing in a perpendicular direction or orthogonal direction?
right.
So you take the Z plus beam and you split it in a different direction. Well, you get X minus X plus, right? Or whatever, maybe Y minus Y plus, depending on how you've oriented this thing. So you're able to measure, okay, this particle is pointing up. It's in the Z plus beam. And then you can split the beam further and say, okay, this beam over here is an X plus and a Z plus. Great. This particle is an X plus and a Z plus. Let's see if that sticks. Go to the next slide. So you put another one of these uneven magnetic fields on the X plus. It should be another Z plus beam that exits it, but no. You get Z plus and Z minus again.
Right.
So these measurements, the X measurement, interfered with the previous Z measurement. So now you have Z plus and Z minus again. So that's peculiar. That means one measurement changed the other.
Because we originally see that the Z minus was actually absorbed from the first one into its sublayer, then the Z plus went on, then it goes through the apparatus rotated in 90 degrees, and all of a sudden you got an X plus and an X minus. The X minus gets absorbed to X plus, then goes through the straight up and down north south, goes to Z plus and Z minus again.
Yeah. And basically what this is referred to as is a non-commutative relationship. So typically when you think about mathematical operations, like you have 1 plus 2 is the same as 2 plus 1.
Right.
Or 3 times 2 is the same as 2 times 3. Here in this case, it's like
right.
Z times X is not the same as X times Z. So this was particularly interesting to a guy you may be familiar with, known as Heisenberg.
That's very interesting. Yeah. Is this related to the Heisenberg thing, or is this something else?
Yes, this is directly related.
Okay, great. All right.
Yeah. Yeah, if you want to go to the next slide. So Werner Heisenberg comes around, and he wants to focus on observable quantities because that's all you can measure, right?
Right.
But as we just saw, measurements can affect our potential to measure other things. So measuring an observable quantity can interfere with other observable quantities.
Right.
So he came up with what he called matrix mechanics and eventually derived what we now call the uncertainty principle, right? Now, you may have heard of the uncertainty principle before, where you can't measure the speed and position of a particle simultaneously to the same degree of precision. There's a lower bound on the precision of both of those things. So the position speed uncertainty principle is just one uncertainty principle. There's others. The one that I showed with the spin, the particle spin, is another one. This is another non-commutative relationship. Position and times speed is not the same as speed times position.
Right.
This type of behavior is characterized by matrices. Have you ever done matrix multiplication in algebra class in high school? Now, it might have been a while, but one thing you may remember is that if you have matrix A and matrix B, it can be that A times B is not the same as B times A.
Right.
They have different results there.
I seem to remember something about matrices and advanced math in college, but my brain forgot a lot.
Yeah. You don't need to remember it. It's just all you need to know is that there's what are called non-commutative relationships.
Right.
Where the order matters.
In short, order matters, people.
And you might notice the little H bar occurring in the white box on the right. That's Planck's constant. Seems to pop up quite a bit.
Okay.
Let's go to the next slide. We have another guy you may have heard of, Erwin Schrödinger. And he took the particle and wave thing and took it to its logical conclusion, at least for ordinary things. We'll get to that later. But he came up with what was called wave mechanics, where instead of treating things like matrices, he treated them like waves. And going by De Broglie's ideas. And postulated that particles behave like waves of probability. So instead of matrices, instead of particles, you have wave mechanics. And he showed that the wave mechanics actually work out to be equivalent to the matrix mechanics, and it's a little easier to work with. So it got things kind of went in that direction historically. And he was able to take from basically first principles the idea of like the hydrogen atom. You have
Right.
concentrated positive charge in the center and a negative charge in the outskirts. And from that, apply this probabilistic wave equation that he came up with. That's the white equation on the right. And get all the shapes of the electron levels in three-dimensional space. So this isn't just rings like in the Bohr model or the de Broglie model. This is the same idea, but applied more comprehensively using our notions of like kinetic energy and potential energy. And you're able to get these hydrogen probability densities. These are what are called the electron clouds.
Right.
And I've done this problem on paper, and it's a beast. Got to tell you that much.
What I noticed just looking at the illustrations is like, as you know, hydrogen from chemistry tends to like to be have a diatomic nature. That's why you usually see two molecules of hydrogen snuggling together. I remember my science teacher talking about how two protons of hydrogen will like stick together because the two elements stick together. Like two electrons are going around two space heaters, kind of like you see in picture 3,1,1.
Oh no! This is just a singular hydrogen atom.
I know, it's cute though. It's actually to me, actually, that's how I kind of see it.
Yeah, these are the different energy levels depicted.
Right.
So like as you energize it more and more and more, what shape does it take? And I saw someone in the chat say s orbitals and p orbitals. Exactly.
Yeah.
Yeah, you can go to the next slide. And that's exactly where I was going to go with this. This is where you get chemistry from physics. So you can solve the Schrodinger equation, that's what it's called, for atoms. And you get the quantum numbers, the selection rules, the energy levels, orbital number, magnetic number, and then you consider things like spin. And we'll get more into that. But yeah, you could see the selection, basically how an electron would move up the energy levels.
Right.
This little snake pattern here on the right. All right, you can go to the next slide. And
antimatter.
Antimatter. Yeah, this is where you get so like Schrodinger. The equation he came up with works great for like ordinary things, but what about really high energy situations where things become relativistic, right? Because Schrodinger's equation is based on Newtonian mechanics, just quantized. But what about Einstein's equations? Mm-hmm. These sort of superseded Newton's equations. So Paul Dirac wanted to characterize Einstein's equations in a quantum way and see what would happen. And one of the outcomes of this is that his equations predicted antimatter, that there should be particles that have the same mass but opposite charge.
Yeah.
And then about 4 years later, Carl Anderson discovers the positron, which is the antimatter opposite of the electron. Sometimes it's also called the anti-electron. So it just shows the predictive power here of this this methodology.
So basically, a simpler thing is the positron is surrounding something called the same kind of thing, but it's going to be containing a negative charge, maybe a neutron core. In other words, the positrons are in the shells outside of the atom. or anti-item.
Positive. So like an anti. They've made in labs. They've made anti hydrogen,
Okay.
where you have an anti-proton that's orbited by a positron.
Okay.
Like that's been, I believe they've even done helium, anti-helium.
Right.
Now the question of why is there more matter than antimatter in the universe is yet to be solved. But so I won't address that here. But when antimatter and matter collide, they annihilate into photons, particles of light.
Right. That's actually interesting.
Yeah. But you've got this, the wave equation. This is the same kind of wave equation that Schrodinger came up with, but made more in the realm of relativity. So things that move very fast, things that are high energy.
Right.
So taking a step back to the wave equation thing.
Okay.
I mentioned that these waves are probabilistic. If you want to go to the next slide, we get into what's called the measurement problem. Right. So this wave function corresponds to the probability of measuring the location, for example. So you have on the left here this position space is like the wave function of a particle, maybe around maybe it's an electron around the nucleus or something. It's a cloud of probability. We want to measure where the electron actually is. So we perform a measurement and, collapse. So you go from big wave to single point. You measure the particle's position. It's now a particle. Congratulations.
Yeah.
But that is instantaneous. So the particle was in many locations prior to measurement. So it's called a superposition. And then it got collapsed down to one location. And that's what we traditionally call a particle. So you go from wave to particle. And then if you let it sit for a while, it'll go back to a wave, right? It'll decohere with the environment and go back to being a wave. It'll evolve. And then you can measure it again, find its position again, and so on, right? So this kind of presents a bit of a problem because people ask, okay, well, is the wave function really a thing? Or is it just some kind of mental mechanism to help us predict what's happening, right? Is this probabilistic behavior inherent to nature, or is this just an artifact of our ignorance, right? This is the debate, right? And the Copenhagen interpretation is that the wave function is a thing, and that when you measure, you collapse the wave function. And we'll get into some of the absurdities that come from this interpretation. I'm going to go to the next slide. So here we'll talk about a little bit more about superpositions. Right? Instead of measuring the location of a particle, let's say we want to measure its spin, sort of like what Stern and Gerlach did with their experiment. But instead of changing the magnet around and whatnot, we want to look at how conservation principles are preserved, even if there's some kind of superposition present. So what do I mean here? So let's say you've got a particle that's unstable, something like an isotope, like a nuclear isotope, something that's going to decay into two other things. Okay, and let's say this thing has a spin of 0, and it's going to decay into two particles.
Mm-hmm.
And because these two particles will have spin, each of them will have spin, their spins will have to be opposite. Okay? So particle 1 could either be spin up or spin down, and particle 2 could be spin down or spin up.
Right.
But if one is spin up, the others spin down. If one is spin down, the others spin up, right? So this is what I'm talking about with entanglement, right? Because of the conservation of angular momentum, these, you measure one, the other. Okay, they're correlated. Now, what you can do is take this scenario where you have up or down, it's unknown, but you know that they have to be opposites. Okay. Let's go to the next slide. Let's say you entangle these two particles, and the way they're entangled is that they decay from a spin zero particle, and so you know that they have to be opposite. You take particle one, you shoot it off to California. You take particle two, you shoot it off to New York. Okay? And then once they get there, they'll be measured. Okay? But the people don't necessarily have to communicate. You say particle one, let's say you measure it, and it's spin down.
Yeah.
Okay? And then you know that the other one has to be spin up.
Right.
Okay? But if the wave function is fundamental to nature, then that means that there's something spooky going on. It could imply that causality is violated. Right? So that means the wave function collapse that I talked about occurred at a speed, can occur at a speed faster than light. So is this violating causality? And so a lot of debate came from this, like are there non-local behaviors? Is causality actually violated? Are there hidden variables? Right? And this sort of thing turns out causality is not violated. You're not actually communicating information by doing this. It's the same if you were to project your shadow onto the moon or something and move your hand's shadow over the surface of the moon really fast. The shadow might move faster than the speed of light across the surface, but you're not transmitting information from one part of the moon to the other. Right? It's akin to that. But are there hidden variables? Are there non-local effects? Well, turns out there aren't any local hidden variables. That was ruled out by Bell. We'll talk more about that maybe in a future talk. But I wanted to talk about entanglement because, if you go to the next slide, it's critical in quantum computing. We talked about quantum computing. I won't get into the nitty-gritty here, just sort of overview. Quantum computing differs from classical computing in that classical computing uses Boolean logic. You have true or false, or 0 and 1. Whereas quantum computing uses qubits, which rely on the superposition of 0 and 1. So something can be somewhere in between. This is characterized by what's called a block sphere. That's the graphic I have on the left. And what you can do is link these qubits, these are just particles with spin, in configurations of entangled particles. So you can have particles that are more than two particles that are entangled. You can have many and in different configurations. And these can be used to process complex calculation.
I'm saying hi, Tiger Kitty.
Oh, yeah, no problem. And you can process complex calculations a lot faster than classical computing. But this only applies to certain types of complex problems. Quantum computing is not going to replace classical computing. It's just going to be an addition. It's going to be a new thing for certain types of problems.
Right.
All right. So to kind of step back, if you want to go to the next slide, this one's a little fun. You guys can scratch your heads about this one for a while. Schrodinger's cat. People probably heard of Schrodinger's cat, and the cat's alive and dead at the same time, or what's going on there? This picture of a cat being alive and dead was not to bewilder you. It wasn't to be like, oh, look at how non-intuitive quantum mechanics is. Wow, shouldn't you be impressed? It was particularly contrived to show how absurd the Copenhagen interpretation is. Because this clearly can't be the case. You can't have a cat that's alive and dead at the same time. That's ridiculous.
Right.
So the question comes, like, what happens prior to measurement? What's the role of the observer? Is the wave function actually real? The solution, there's many possible solutions. We don't really know which one's true, but there are solutions to this. One is that one is pretty obvious, that the observer and the universe are part of the wave function too. After all, you're made of quantum particles. You're not some other substance. You have what is called decoherence, where the environment interacts with the alive or dead cat and gets entangled in that way. And then the observer is entangled with the environment and the state of the cat.
Right.
And this leads into the many worlds theory that you might have heard of, where every outcome like this splits the universe into different outcomes. Like there's a universe where the cat's alive, the universe where it's dead.
Right.
That's where that comes from.
Right.
All right. So if you want to go to the next slide. So in summary, we've gone from atomism with the ancient Greeks to subatomic physics just over the course of a couple thousand years, perhaps uncovering more of the nature of reality. There's established theory, but there's still open questions that might be answered in a lifetime, maybe not, I don't know. But these quantum phenomena are present in everyday things, from chemistry, medicine, electricity, solar power, even classical computing and quantum computing. It's everywhere. I mean, you are a quantum thing too. You're made out of atoms. There's other things I could talk about here. I have like a one backup slide if you wanted to check it out.
Okay.
Just the honorable mentions. I'll just go to the next slide. Where you have, might hear the phraseology of quantum field theory or quantum electrodynamics. You might hear that. Accelerators and colliders, like the one over in Geneva, Switzerland, where you have particles being accelerated to near the speed of light and being collided, and then looking at the collision to try to figure out what's going on the fundamental level, exploring the fundamental forces like electromagnetism, the two nuclear forces, and gravity. You may hear the term quarks. I did not talk about quarks at all. Turns out protons and neutrons are also composite. They're made of quarks and gluons.
Yeah.
And then there's the terms leptons, fermions, and bosons. Leave that for another time. Unification. Of course, dark matter and dark energy. Those are some other words you might hear from time to time adjacent to these topics. I hope this gets you a little more comfortable with this phraseology, with all the vocabulary, makes it a little less scary. And I'm hoping to do sometime in the future, maybe like a primer on calculus, because one thing that's essential for physics is being able to do calculus. And to give you a little bit of comfort, calculus, I tutored for many years, and I found that folks that get stuck on calculus only get stuck on it because they're stuck on algebra.
Mm-hmm.
The calculus part is actually easy once you got your algebra down. So I might do a primer on that sometime in the future, so stay tuned to that. But yeah, that's all I got here. I hope you guys enjoyed this.
Yes, thank you very much for coming out, by the way. And I wonder if anybody has any questions they'd like to ask. This might be a good time for you to ask them.
Yeah, I don't know how late you're going, Michele. You need to eat up the whole hour.
Let's go see what kind of questions we have, if anything. Let me just slide this chat around here. Okay. It's of course Brian Case talking about stuff like integrals. Hell yes. Strange. I hope Michele has him as guest more often, says Grizz. Yeah, we'll try.
Yeah, I'll be happy to be on more.
Mob Society says W stream. Brian PC says very helpful. Brian
I'm happy to hear that.
PCK says he has a question. Let me just
Oh,
slide
yeah?
this chat over here. Okay.
Cool.
What's your question, Brian K? I'll just slide this chat over to my other screen here so I can see it. Well, yeah, you know what? Actually, that's, not a bad idea, guys. If you could do that, it's really, first of all, I want to thank Wafters for coming up here and taking the time to prepare this presentation. So, yeah, it would be, one unit of currency would be nice. Don't have to send me thousands of pounds or dollars, just like maybe $1 question if you really want to get into the really meat potato questions.
Let's see, we got the uneven magnetic fields. Were those same thing as the Hallbach array? No, not the same thing, but similar kind of idea. The Hallbach array is like an arrangement of magnets that you can put together where the magnetic field is only on one side of it instead of all around. So it's an interesting geometric thing. Similar idea, but it's not. It was not a Hallbach array used there.
Yeah.
What was the most impactful discovery in the list of historical figures that you listed? I'm always gonna side with my boy Einstein. He was literally like my role model as a kid. I had like a poster of him on my wall and everything.
See, a lot of the stuff we talk about tonight is really new to me, so I didn't really have a very deep understanding of a lot of that. I took chemistry in college, and I was like, that was confusing enough talking about moles and,
molarity and molality. There's two of them?
Yeah.
I remember learning that. I was just being frustrated. Why is there two?
Yeah, exactly. And then my brain, after all these years, was like, oh, crap. Thank you so much. Sarah Turk says, very informative. I even knew a few of the facts, she says. Well, glad you responded, and thank you for being here. And I hope you enjoyed a good time with the show. I think it was interesting.
Don't answer questions that weren't answered.
Tiger Kitty said the answer money. Okay, thank you, Tiger Kitty.
Thank you, Tiger Kitty.
So here's the thing that's interesting. We're talking about things you were talking about with elemental electronics and semiconductors. And Usagi Electric has been talking about the fact that the semiconductors are actually kind of still sensitive to light. He was talking about photodiodes. Talking about how one is his Bendix G15 that they're using a photodiode to read the paper tape. And just as his home computer design UG1 system is using same photodiodes to read tape. But he said even a signal diode, a regular glass signal diode, if you aim a flashlight at the junction, you will actually generate a small signal.
Yeah, you'll generate a small voltage.
Yeah.
Photoelectric effect, yeah. Yeah, the photons from the flashlight hit the atoms in the junction, and energize the electrons and eject them.
But
And
right
that
now, he's
creates a
been very
charge
lucky. He's got access to a Bowman spectrogram, I can't even say that word right. Spectroscopy machine.
Spectroscopy? Is that what
Right.
you're trying to say?
He's got a
Yeah.
Bowman. He's got an older Bowman hooked up to his P2P11 there, and so he put a small little photodiode into a jig and was actually showing which signals were being passed based on the different levels that the Bowman could do, which was kind of interesting. He said mainly it was more infrared with some of the regular yellow wavelength for that one photodiode.
Oh, so he was able to, basically do spectroscopy by measuring the different.
Right, and find out what signals were most likely to be easiest to read from a light source going through the paper tape. Right.
Interesting. That's cool.
Yeah. Any other questions?
You were joking about the super chat question.
I saw that, Grace, but actually it's not a bad idea, though. Well, here's a question you can answer for free. Did you guys enjoy what you heard today? Did you enjoy being here, Wafters, discussing this?
Yeah, it's fun. It is it's a blast for the past for me.
Yeah. Well, let's talk about something a little more blessed to the present. You got this, which is a weather thing, which is more of my forte. You got the super El Nino that's forming.
Yeah.
And we have, according to Snyder reports, it said we have a major heat dome effect coming up into the East Coast and parts of the South, including Texas. How do you think? How much do you think is being accelerated by the super El Nino?
I haven't kept up with weather news at all.
Actually, up here, I'm a little bit up on this than you here.
I think so. But yeah,
But then atmospheric sciences is
El...
more my thing. So
I know about the super El Nino.
Yeah. Think of Super Texas Barbecue, because that's exactly where it's really going to be cooking. Because
I know France is cooking right now.
Oh, yeah. They already had a power failure. They blew a fuse.
Yeah.
Yeah, because too much demand for fans and trying to cool. And, of course, people have succumbed to heat stroke in France.
Yeah, I mean, Europe is not used to the kind of swings in temperature that we get here in North America. Like, they don't even get tornadoes over there typically. Like, that's like we have the crazy weather.
Yeah, and then of course the people that came over here because of FIFA are really kind of enamored with the fact that we have personal cooling devices called air conditioning.
That's true. Star Turk's pointing out that Keldoge is more the weather guy. That is true.
Yeah. Right, he's more the weather guy, yeah.
I got to tell you, I tried to make you a theme song for this. Do you remember Bill Nye the Science Guy?
Yeah.
I tried to get Suno to make it be like Michele the Science Gal, but it just wouldn't cooperate with me.
Oh.
So if someone's better at Suno than me, please make that.
I probably could work on something. Maybe something more generic. Let's explore the scientific world with Wafters. Oh, thank you so much. I think I just saw a follow. Thank you so much. It's going to be 91 next week. Yeah, it's going to get toasty. I was just talking to Craig Sr. about that this afternoon. His wife are, of course, being a little older. The heat is not exactly going to be their friend. It's going to be hard on a lot of people. At least I'm kind of better off than some because at least I'm not living in a place where there's a heat island effect, or at least not that much of one. Which basically is this, guys. It's very straightforward to understand. If you have a lot of asphalt, it basically absorbs energy, infrared energy, and then it later radiates it back out again. So that means that the heat is staying around for quite a few hours after the sun goes down.
Asphalt tends to do that. Yeah, I wanted to get the song to sound like the Bill Nye song, and I kept prompting it with like jock jam noises, jock jam vocalizations, and it just wouldn't do it, and I was not satisfied at the outcome.
Well, if you send me the lyrics, I can try feeding it in.
Sure. Yeah. I just replaced Bill Nye the Science Guy.
Right.
Yeah.
What I like to do is I try to be a little more maybe a little more generic because we're going to be covering a lot of different sciences on a simple level. This is a pretty high tech one. This is really top up there, but even we could just cover standard chemistry.
Oh, sure.
You know, for example, there's that what is it? Trifluorine something that is one of the most scary fluorine chemicals in the world that eats through concrete, burns glass.
Oh, yeah. It's something. It's nearly a chemical that can't really be contained. It needs.
Not really. No, unfortunately.
I think there's some plastics that can contain it.
Yeah. And certain types of steel coatings can kind of help prevent it from, because it develops kind of an inert, but it's kind of a very sensitive thing. The fact is, it can eat through concrete floors and keep on eating like a Taurus.
Yeah. In theory, you could make a substance that cannot be contained. Like if you mix that with like...
let's hope science doesn't go there yet. I don't think we're ready for that.
Well, it already exists.
Right now we're talking,
exists.
But just like you're talking about matter and antimatter, that's scary enough. Imagine what would happen if.
Luckily, we can only make antimatter in very small portions.
Well, maybe that's a good thing. Aye, Captain, she can't swallow that. Talking about the molecule that was basically, I think the planet killer. Planet killer, right? Remember that thing they eat planets for dinner?
No, from which sci-fi franchise?
I think you know what the concept is. Basically, this is ancient creature or something in space that eats universes and planets.
Oh, okay. Yeah.
And then, so they basically found an old disabled spacecraft that was kind of nearby. And so Scotty managed to rig the magnetic containment for the antimatter to basically go supercritical inside the maw of the monster and blowing it to bits.
Gray death from nanobots.
Yeah. Brian K says anemonic acid. Yeah. Crime for you says, is it really you? It's higher than 2 rides effing in a wood sock here today. Next week it's gonna be mild. Well, that'd be nice for you to get a break. Because right now, I know that the West Coast has been sitting like a grazed on a barbecue, roasting on a rotisserie. But hopefully, you guys are going to get a little break. Unfortunately, Texas is going to be like a big, giant brisket cooking. And unfortunately, it's not meat. It's going to be a problem, especially because the power grids, they say the East Coast is going to get slammed, according to Snyder reports. as I said, I'm very fortunate. I do have at least a backup energy system to keep some things running. Not everything. I can't run the universe, but I can run my air conditioner for an hour and 20 minutes, but not much else. Or I can run, the studio lighting and maybe a couple cell phones to do a 4 or 5 hour or 10-hour show. So,
seeing what would happen. I'm asking Copilot, what would happen if you mixed fluoroantimonic acid with piranha solution? And it says extreme hazard. Extremely dangerous. Piranha solution, by the way, dissolves anything organic.
Oh, okay. So anything that contains carbon.
Yeah,
carbon molecules, which is organic.
You can watch videos of people dropping like a hot dog into piranha solution, and it dissolves it.
You should see what fluorine gas does to raw chicken. See, I watch some science channels like Now Red and things.
High risk of explosion, severe burns, and toxic fume release. Yeah, I imagine this is something that wouldn't be able to be contained very easily. You just have to let it react with the environment till it stops reacting, till there's none left.
What about the power of hydraulic reactions used for rocket engines, like containing hydrazine and tetranitric something that is used for propulsion, like in outer space? For the hypergolic reaction, that is really creepy and scary. I mean, the hydrazine alone will kill you. The nitrogen stuff, nitrogen oxide gas will kill you too. So either way, you're dead before you hit the floor.
Yeah, it basically ignites on contact with.
Yeah. Yeah, I watch some weird stuff on YouTube. Any more questions? Claim for you says, when did you realize you were famous?
I don't think any of us are famous.
I don't know who he's talking about, me or you. Anyway. So Brian K said, we have some massive glass ampules, rubium, and I always want to smash one of them on the rocks outside just to see what happens. I don't know much about that mineral. I mean, I think that's one of the radioactive elements. Rubium. There's 115, I believe, on your periodic chart you showed. There's 115 elements in that chart. Yes, I did count. So,
I mean, any element can be radioactive because it can always be an isotope of that element.
Right.
But, it's slightly radioactive on average. Yeah. It's an alkali metal similar to potassium or cesium. Okay.
Now, potassium and cesium is scary when they combine with water. Those guys really go boom, even more so than lithium.
Yeah, they're in the same column in the periodic table. They have a very similar reactivity. Yeah.
Right, the first column, right, and highly reactivity. That's what the people don't realize with the way the periodic table is set up. Is by the time you get to the center of the table, let's say like you get the things like gold, silver, aluminium, mercury. Those are kind of fairly relaxed, not super highly reactive. And then you get into the other ones that are probably the most tame of all the noble elements.
Yeah, things that
Cyan,
don't react with anything.
neon, right? They hardly react with anything.
And that's what Mendeleev did, like arrange things according to their mass and reactivity. And that's how you got the periodic table. And it actually had predictive power. It's able to fill, there's some blank spots and you're able to fill that in.
Right, carbon-14 dating, yeah, that's real. Yeah, that's why we use it. It's not the only kind of dating. It is the most common form of carbon-14 dating, but it's not the only one.
Yeah, there's other types of dating, yeah. Speed dating.
Mm-hmm.
Blind dating.
Where do you think this science is going to go, or how do you think far we're going to progress, you say, in the next 40 years? What's your opinion?
In what, in like the quantum stuff or just in general?
Yeah, quantum and chemistry. Let's bring them both in.
Oh, yeah. I think if investment in science keeps up, I think we'll have another particle collider that is even larger than the one in Geneva. And we'll start to be able to probe even further, perhaps experimentally start testing if string theory is based in reality at all. Stuff of that nature. Maybe discover some new
I know
particles.
that, Brian K. I know that because fluorine and bromine and chlorine are halogens, and they certainly are very reactive.
Maybe we'll
Somebody
find out
says chlorine poisons water, fluorine causes it to explode. I wouldn't want to breathe bromine either. Yeah.
Maybe we'll find out what dark matter's made out of.
Yeah. Maybe you could finally answer about, what is dark matter. That would be kind of interesting if we could figure that out, because they say half the universe is dark matter.
Oh, more than half.
Yeah. More than half, really.
By mass, yeah. Large portion. It's just the substance that only interacts gravitationally, as far as we know.
Yeah.
And we don't have a reliable quantum theory of gravity yet, so it's hard to say. But I think those will be figured out around the same time. That's my.
Wouldn't it be kind of fascinating if we could find a way to create a reliable, inexpensive, affordable gravity, so that we could actually give spacecrafts something similar to a normal Earth One gravity? I mean, that'd be nice for future space travel. For reasons.
Yeah, I think we're a long way off from that sort of thing, because we don't control. We don't even know what gravity really is.
Right.
Exactly. So you have gravity is modeled as the bending of space-time in the current paradigm, but then you also have quantum theories of gravity, where it's mediated by a particle called the graviton, which is yet to be discovered.
Right, I've heard of gravitons.
So we don't even know.
Could gravity be somehow tied to magnetism? Because
yeah, it's thought that it is. We just don't know how exactly. We think all the forces are interrelated. Like electricity is related to magnetism, and they got merged into electromagnetism.
Brian PC asks question. There are rumors around the internet about the Hadron Collider starting a black hole through the Earth. Is this true or false?
False.
False. Thank God. You don't need that.
I mean, if there were black holes created within a collider, then there would be black holes created all the time, because the energies at which the colliders that we make collide particles are much lower than the particles coming from outer space smacking into the atmosphere.
Right.
So if the Large Hadron Collider had the capability of producing like a dangerous black hole, that would have already happened in the atmosphere at some point. We would already be dead.
Right. What about I've heard rumors in the past about 2017 that they thought they had accidentally created a micro portal to another dimension, but it was some years ago. But is that possible with the amount of energy that the Super Hadron Collider actually uses?
What that's talking about is that perhaps it's not like another dimension like in Ninja Turtles. It's not. There isn't like another universe you're passing into. It's
more like they think they saw that they said they observed there was something on another side of a very, very small portal. And I'm not talking about the one in the sky. That's something else. I didn't know about the swirly thing above Geneva. I don't know much about that either. But yeah, I think they said that they saw kind of through another dimensional thing, but then they said that's not something that came through from that dimension into ours. I don't know if that's true.
No, that's not true. That's okay. No, nothing came. There was no like portal like in a sci-fi or anything like that. In physics, when people talk about portals, like you'll hear, a portal to dark matter or something like that. What that means is that there's potentially either a theorized or measured connection between ordinary matter and dark matter. Like, we found the connection between the two. That's what they mean by portal. There isn't like a literal portal from like, the cake is a lie type portal.
Do you think it ever be possible that we will one day find a practical way to create stable wormholes between points in space?
Well, and the funny thing is that entanglement that we were talking about, Einstein and folks thought that entangled particles are connected by a wormhole.
Okay.
It's called the EPR paradox.
Okay.
So there may already be wormholes all over the place. Whether we can, enlarge them so that we can like pass through them, I don't know about that.
That's a good question. I don't know. Well, I'll say one thing. You certainly got a bit of a crowd tonight. I saw we were pretty high with the number of views, which is amazing for a show that's clearly not a typical content for my viewers. And I think they did enjoy themselves.
I'm glad.
Again, I want to thank you for coming up here and being here next week, 8 o'clock again. We'll see if we can get something else going.
Sure. Yeah, you can pick an idea for a topic and I can expand on it or whatever. We can go nuts.
Okay. I'm sure me and Sabine Hasselfender will come up with something. All right, so thank you very much for being here tonight. And you can give me your lyrics of the song, and maybe I might tweak it a little bit and find a way to make the thing make some music with I Love Song AI.
That sounds good.
All right, you have a nice night now.
You too, Michelle. Thank you.
Yeah. Don't forget, M60 and you can be live tomorrow also for Tech Talk.
Oh yeah. Yeah. Stay tuned for Tech Talk.
That's tomorrow night at 7 o'clock, or maybe 8 o'clock, whichever one. I mean, M60 can let me know if he wants to change it to 8. We could do that. So you have a nice night now, by the way.
Hey, you too, Michelle. Thank you again.
Yep, end call. Bye-bye. And that was really fascinating. Honestly, I'm not going to lie. Some of it was way over my head. But I'm probably going to be thinking about this stuff tonight when I'm trying to sleep. Like I said, Michelle, if you ever want to talk, you have my Discord. Yes, I do. I do have your Discord. I am still in your Discord. And this is actual meat and potatoes, yes. But we try to keep it relatively simple because we know that not everybody here may have had a high college or a a high level high school education, and it just makes a difference for everybody. But for now, let's get ready to wrap it up. By the way, tomorrow is going to be still pretty warm, not too excessively hot, but be ready for what's coming, because I did look at the extended forecast from my area for the next week, and it does look like we are going to get close to 30 degrees Celsius by the end, middle of next week. So it's gonna get Quiznos, toasty. So let's get the blessings out. May all of you guys have a happy and safe day. Stay out of trouble. May your nights be pleasant. May nights be full of particles. May you have dreams of covalent bonds, some nuclear physics, and God knows what else. You might come up with the next device that does something great. Be surprised how much when you sleep, sometimes something comes up and you get the aha moment. Go, I just recognize it. Now I understand what's going on. Woo! You start. That's true. It could happen. But either way, get out there, get some sleep, and have a good night, and we'll see you tomorrow. The service is over. Time to go. Peace, kind, love, and don't forget to be excellent to one another. Party on, dude, and like and share. And we'll see you tomorrow morning at 10 a.m. Until then, good night. Bye-bye. Bye-bye, guys. Bye-bye.
Michele and Maria Lumi, I will always be there for you. Michele, never stop believing in yourself. Go out there and show the world what you can do. Go kick some ass and have a good time doing it. I love both of you so much. I love how far you have come on YouTube.
In the samba's embrace, she finds her way. Twisting and turning, she won't let things sway. With love for the music and fire in her soul, she dances through life, her heart in control.